p35, we are concerned with taking a base region or a region in two-dimensional space and revolving it or rotating it around an axis. All right, so what I'm going to do is take this is the same example from, or at least something similar from a couple of pages ago. So I'm going to just sketch it out real quick. Just take a second and do that. All right, so the cube root of x is going to look something like this. And x equals 8, vertical line. All right, and so if we wanted to, we could figure out the area of this region. Right? It would actually be pretty simple. But what we want to do instead is actually take this region and spin it around the x-axis. All right. So what we do is we take an arbitrary rectangle over the interval. Those Riemann rectangles, if I can draw it correctly, that would be ideal / necessary. We're going to take that rectangle and we're going to spin it around the axis. Alright, so I got to get a little cute with the positioning here, but this is what we would get, or at least in part. Alright, so this, I mean, we'd also get a rectangle that's pointing directly out at us, one that's pointing at a 40-degree angle, you know, so something that's kind of floating up over here, you know, something pointing directly at us, something that's pointing this way, this way, this way. It's kind of hard to imagine this, but this is supposed to be a top view of a circular figure. All right, what's really happening is that this is getting spun around the axis. All right, and it's creating something that would be circular. All right, so what I can try to do is, well, first off, I'm just going to do something like this, you know, just kind of live with that. All right, this is the revolution of it. That's the bottom end of it. All right, so I'm just kind of creating what would be sort of like, you know, the semicircular slice. Just we would need essentially two of them to create a circular slice. All right, because that's what a volume of revolution is. It's going to be a circular slice. Just part of it, you know, it's not just going to be emerging from the page. Part of it's going to be going into the page. All right, so I can try to do a perspective drawing. So what I mean by that is I'm going to do a perspective drawing. I'm going to try to make it look good enough for you to actually understand what I'm going for here. All right. I'll try not to chuckle too much while I'm doing this, because I know that people are, and there I am chuckling, people are relying on me getting this right so that they could have a fighting chance of understanding what the heck I'm talking about. So what we have here again is that rectangle, and I'm going to try to again do it using a perspective. All right, so that's that rectangle. Now it's going to be spun around the axis, all right, the x-axis here. So you're going to have part of it living over here. All right, then emerging from that is going to be a semicircular region. All right, so I'm going to draw something semicircular coming out of the page. But then it'll also be semicircular going into the page. And that's usually where my diagrams fall apart. But what I'll do is I'll try to color in a face of this just so you can kind of see what I'm going for. Alright, now it's going to look elliptical here because it, like I said, it's a perspective drawing. So when you draw, oh, that's fun. Alright, well, when you draw a circle with perspective, it oftentimes looks like an ellipse. Alright, I should have chose a different color, so that's what I'm going to do. I'm going to choose a different color. And so this would be what you would get if you revolve that region around the axis. Alright, so, you know, it's not perfect. And in fact, I might be better served by just really kind of shading in the one side. But it's really just those rectangles that's being spun around the axis that's giving us this circular slice. All right. Now what we would have to do is repeat this process infinitely many times. All right, infinitely many times over the requested interval. All right, but just like we did with the slicing, we would want to figure out the volume of just one of the figures first before we get into that. All right, so what is the volume of a circular slice? The volume of a circle is going to be pi r squared times, well, that's the area of a circle. The volume of a circular slice is going to be pi r squared times whatever the depth is. Now in this case, that depth is associated with a change in x that we'll call dx. All right, that thickness here is dx. All right, but it very well could be oriented the other way, so it's possible that it could be a dy. It's just, in this case, it's a dx, right? Because we're revolving it or rotating it around the x-axis. All right, so as long as I can come up with a radius, I'll be in good shape. Well, the radius appears to be the length of that rectangle. All right, so we'd be looking at pi times y squared times the thickness, which is dx, over the interval of 0 to 8, because that's our bounded region, x equals 0 to x equals 8. Knowing that y is equal to the cube root of x, we could say from 0 to 8, pi times the cube root of x squared dx. All right, and if we evaluate that integral, we'll have our volume. So math 9 from 0 to 8 pi cube root math 4, pop in the x. It always looks a little weird. I'll put the power of 2 in there with the cube root. It just looks like it's the pi squared, pi cubed, but actually when I put the power of 2 in there, it started looking all right. All right, so I just reversed it so that it was a little bit more convenient. Hit enter, and we have about 60.319 cubic units. All right. So you can do it that way, or you can pop it into Desmos. So I'll put in the pi. I'll write it as x to the 2/3 this time. dx, and you get the 60.318. The area was bounded, or I'm sorry, the bounded area was rotated around the y-axis. All right, so I'm going to take my diagram, or at least most of it. I'll take the whole thing and then trim it. Trim some of the stuff. Alright, so the axis of revolution is going to be the y-axis. So all of this goes away. All of this goes away. Alright, and so what we want to do is spin this region, and we're done with the x equals 8 also. It's like, which region are you talking about? This region, because now we're going to incorporate the y equals 2. Alright, so the bounded region is going to get spun around the y-axis. Alright, so we're talking about this little rectangle here forming the radius of a circular slice. Right? And so really the best way I can kind of get this idea across is to say that a circular slice is the semicircular cross section just essentially doubled, right? But then also reflected over the appropriate axis, right? So, or more appropriately, it really isn't a reflection. It's more like it's expanded to like the radius itself is reflected over the axis first, and then you create your semicircular cross sections. All right, so we'd have this part going into the paper. All right, and then you'd have another piece of equivalent length in terms of the radius. I'm going to try my best to make this not terrible. All right. This other piece is going to now get kind of attached. Alright, so that one maybe not so good. Recommendations: art, studio art should be a requirement for math teachers. So you have this piece, this other semicircular cross section being tacked on to the one that's going into the paper. So this one's emerging from the paper. So coming out of the paper, going into the paper, and then there you go. All right, and so we have this radius R, poor quality R, so let me fix that. Now that R is consistent with a horizontal distance from the y-axis to a point in space. All right, so every point in space, again, I say again because I've been saying this in video after video after video, hoping to get this idea across. Every point in space is an x value, comma, a y value. The x value is the distance from the y-axis. The y value is the distance from the x-axis. All right, so I've said it repeatedly, but this I think might be the first time I'm actually writing it, right? Because now it's becoming important to the point where I don't know that we can proceed without having a good firm grasp on this idea, all right? Because when it comes to areas, it's like, all right, just integrate the function and most of the time you're right. Here, it's more than that, right? And it's going to get more evolved as we go forward. All right, so if you want an area of a circle, we're looking for a pi r squared. We're going to take that and multiply it by the depth, all right, or the thickness, all right, and so now that thickness is corresponding with a y value, so that's a dy. So pi r squared dy. Now that horizontal distance, right, is distance from the y-axis. Oop, that's a little too thick on the marker, or on the highlighter. Distance from the y-axis is x, which is telling us that r and x are the same thing, right? At least in this situation. So pi x squared dy. That's going to give us the volume, because area times the thickness, incorporate a third dimension, and now you have volume. This is going to give us the volume of a circular slice. Right? Now I want all of them. All right? I don't want just one. So I can kind of cap this back on. Hopefully it doesn't look too crazy. Not too bad. All right? I want all of them. So I'm going to integrate from beginning to end. Beginning to end of what? The bounded region, which starts off at y equals 0 and goes to y equals 2. So from 0 to 2, we know we're working in terms of y because that's our variable of integration. So pi x squared dy. So now it's a question of, okay, well, we have an inconsistency between the variable of integration and the variable contained within the integral. Y is equal to the cube root of x. If I cube both sides, I get x in terms of y, right? So from 0 to 2, pi times y cubed squared. So from 0 to 2, pi y to the 6th dy. I mean, this is reverse of the power rule. You can do it by hand. You can put it in the calculator. Either way. And some people like to do it both ways just to have that extra layer of security. I'm just going to pop it in. This is one of those in-between cases where it's like, it may actually take longer to type it into the calculator than it would to do it by hand. I'm actually going to use the variable y here, just because I want to. Feels nice. Feels nice to have it in the appropriate notation. A little extra comfort. So 57.446 approximately. Again, cubic units. All right. Get my Desmos involved and a little double checking. So integral from 0 to 2 pi y to the 6th. Close it up and pop in a dy. We get the same number, so at least we got a quick double check going here. All right. So yeah, I have these diagrams lying around here just to kind of show the act of taking the two pieces and putting them together. It's just it's not quite, it looks all right, but that's essentially what's happening up here. I'll just kind of pop it in there. For posterity. There we go. Good enough. All right. So what if the area bounded between the cube root, x equals 8, and the x-axis is rotated around the line x equals 8? All right. So now we're getting fun. What would be the volume of this solid? All right. So vertical axis of revolution, but this time it's the line x equals 8 rather than the y-axis. All right. So we're still going to have to figure out what our radius is. All right, so we're revolving around this axis. All right. And so if that's the case, it's kind of like we're looking at it from, I'm just going to do a quick rotation here. We're looking at it from this perspective, kind of. So we want to have horizontal rectangles. And a general rule of thumb is when you're dealing with this method called the disk method, because they are circular disks, I can't. That's obviously in my not in my speech wheelhouse to say that disk method, circular disk, DISKS. Um, you want to have your rectangles. That's not a rectangle. You want to have the rectangles that represent the radius of your disk be perpendicular to the axis of revolution. Alright, so copy, paste. Gotta remember to turn the marker on. Alright, so just gonna draw, again, a little arc, attempting to illustrate that it's creating a semicircle going into the page. And then I keep doing that. I'm going to draw another rectangle. Really, it's not so much a matter of coming up with a rectangle as it is the arc. And there's software out there that'll do this for you, and it's all wonderful. And I'll show you later on down the line what that looks like. But for now, I found that it was helpful for me to get a firm grasp on what this stuff was all about by at least trying to draw it. You know, I'm not going to require you to draw the figures, but I feel like it helps in allowing people to understand the concept. If you disagree, you'll let me know. All right, so what I need is the length of the radius. So that radius is the length of one of these rectangles, but I can't just call it X or Y, all right, because it's not attached to the X-axis or the Y-axis. But what I can do is draw a line segment connecting the Y-axis to the axis of revolution, because we know that that's equivalent to 8 units. Make this a little thinner. So this is 8. Now, the piece that we don't want, just shy of the piece that we do want, that's actually X. So we can work with that. It's useful information. So that's X. The whole thing is 8. All right, so this whole distance here is 8. If I want the length of the line segment in between the two, and actually I could probably move that up a little bit, more like up here, and get rid of that, just to keep it consistent with the rectangle I drew. Then all I'd have to do is subtract X from 8. So we'd be looking at 8 minus X. That's the length of the rectangle. All right, that's actually our radius. All right, and since we know that the volume of a circular slice is going to be the pi r squared multiplied by the depth. The depth is a y movement, so dy. We're really looking at pi times 8 minus x, the quantity squared, multiplied by dy. I'm going to integrate that from the beginning to the end of that interval, which starts off at 0, y equals 0, and maxes out this intersection here when x is equal to 8. Since the function is y equals the cube root of x, put in an 8 for x. The cube root of 8 is 2. So we're going from 0 to 2, or quality 0 to 2. All right. Again, we have a disagreement between the variable of integration and the variable in the integrand. So I'll make that substitution because we know that y equals the cube root of 8 corresponds to x equals y cubed. So the integral on the interval of 0 to 2 of pi times x minus, or 8 minus x squared is going to become 8 minus y cubed squared dy. So now it's just a matter of integrating. So math 9. On the interval of 0 to 2, we got a pi. We got an 8 minus y. I'll use the y again. Raised to the third. You could use x instead if you want. Quantity squared. So pi r squared dy. And we're looking at about 258.508 or 508. And that's units cubed. All right, so we could double check on Desmos. I'm just going to steal the work here a little bit. 8 minus y cubed squared dy. And so there we go.